All right, let's hit some forces on an inclined plane, which is talking about objects on a ramp. So we've got a few questions we'll try to get through with this. So again, as you take some notes, I would encourage you to make sure that you're answering these questions and give yourself enough information so that if you saw these questions again somewhere, you would kind of know what to refer to. So we're looking at just basically, what's an inclined plane again, if you've forgotten. How do we draw forces on an object on an inclined plane? And yay, how do we do some math for an object on an inclined plane? So our main vocabulary with this one today is inclined plane. Ultimately, there's not really a whole lot of other new stuff going on. There's some different forces, but we'll get to those in a moment. So an inclined plane, just a fancy name for a ramp. We'll get to those when we talk about simple machines again. But when we have an object on a ramp, you probably understand the fact that if you change the angle or the steepness of the ramp, then that's going to have some effect on how the object on the ramp is able to move. Whether you were pushing it up or pushing it down, if we change the angle of the ramp, it would make it easier to pull it down, or it might make it harder to push up. So effectively, the steepness of the ramp has kind of a big effect on how we experience the forces, even though the weight of the object doesn't really change. So the second question was, how do we draw forces on an inclined plane? And you can see the diagram that I've got down here, and there's arrows kind of going all over the place. So we want to kind of make sure we understand what these arrows are. And again, there's a good chance at some point on an assessment, this is the kind of thing you see to see, is it labeled correctly, or are we looking at things right? So when we have an object on an inclined plane, it still has a weight to it, and a weight is a force, and forces are measured in newtons, and the weight is still going to be drawn straight down. So you'll notice that it's just like anytime we were drawing an object on a flat surface, the weight is going straight down. However, again, as we change the steepness of this angle, then it might make it either easier or harder to move down the ramp. And so kind of what happens here is as we change this theta, the angle that we have here, the blue line and the green line end up changing a little bit, although the red line never changes at all, right? So we can kind of break this weight out into two different components. There's the component that kind of pushes into the ramp, and there's the component that wants to kind of slide down the ramp. And again, changing the angle changes either how much of it is going into the ramp or how much of it is coming down the ramp. So this funky little sign right here, this force is the parallel sign, and this parallel force is the force pushing down the plane. And so you can see that it's labeled blue. It's called parallel because it's parallel to the ramp. Force with the perpendicular sign is what's making the right angle. Perpendicular means the right angle. And so this is the force that's pressing into the surface of the ramp. And you can see that it's going to be making a 90-degree angle that we have there. So that's kind of how we draw it. The weight's going to go straight down. The perpendicular force is going to run, the parallel force is going to run parallel to the ramp. The perpendicular force is going to go straight into it. So sketch these out. See if you could get an idea of drawing the forces on each of these three things and how they would change if you were drawing all the arrows that you had. So I want to pause the video for just a second, sketch these out, and see what it ends up looking like. So when you've moved these along, hopefully what you end up seeing is this black line on A and the black line on B and the black line on C. That's going to be the weight of the object pressing down. And again, notice it still goes straight down. As we go from A to B to C, kind of what you notice is the angle of the ramp got steeper and steeper and steeper. So angle A was kind of a flat ramp. B was in the middle. C was very steep. And what you see correspondingly is that the red arrows change and also the blue arrows change. So notice as it got steeper, the red arrow was the longest to begin with, but it shrank. And so again, there's not as much kind of a force pushing into the ramp as it gets steeper. Correspondingly, the opposite happens. The force that's parallel to the ramp increases, and it kind of wants to go down, straight down a little bit easier. Right. So again, the weight doesn't change. So the line that we're drawing straight down is still the same line. However, the parallel force is going to increase as it gets steeper, and the perpendicular force is going to decrease as it gets steeper. There should be a fourth force that's drawn on here, and it's our normal force. We've defined this before, but the normal force is the force of anything pushing up on an object. So in this case, it's the force of the inclined plane pushing up on the object, and it's still going to be perpendicular to the surface of the plane. It basically is an extension of the parallel. We got a cat meowing over here. It's an extension of the perpendicular force. The perpendicular force goes perpendicular into the ramp, and the normal force is going to go perpendicular away from the ramp. Right. It's going to be in the up direction. And again, generally the normal force and the perpendicular force are equal and opposite. They're going to cancel each other out. All right, so if we're given this, here we go. How do we calculate things? So this is where trig functions come in again with sine and cosine. So if you look at the way this is drawn, you can kind of roughly make out that there's some triangle thingies going on here. One of the weird things about it is that you'll notice on this drawing that there's actually two different thetas that are on here. So the normal theta we usually talk about is this theta, but mathematically this angle and this angle end up being equal to one another. So if we know this angle down here, then we technically know this angle. And then our triangle actually becomes the one that's drawn here as we go down. And so again, the adjacent side to this angle, or the side that's adjacent, ends up being our perpendicular force. And even though the parallel force is over here, the length of this triangle, the length of this side is going to be equal to the length of this side, which means that technically I can calculate the parallel force by looking at the opposite side that we have there. So just some kind of, let's say basic trig, but some trig that we've done before. So notice again on the image, the parallel force is opposite the angle. So again, even though the angle is down here on the original diagram, it's going to be the same angle that we have here. The perpendicular force is the one that's adjacent, and so we can use the cosine function to be able to do that. So some example questions. If someone was parking her 19,000 Newton car on a hill with a 24-degree incline, can we calculate the component of its weight? What's pressing into the hill and what's trying to go down the hill? All right, so how would we go about trying to set this up? Again, I always encourage trying to draw things out to begin with. So if we've got a ramp, right? We've got an object on the ramp, which is the car. We've got an angle here, which is 24 degrees, right? And again, so if you want to draw our forces out, so we've got the weight of the car, which is going straight down. That's our 19,000. And then we've got an arrow that's going to go straight into this. This is going to be our perpendicular force. And then we've got an arrow that's going to be going down, which again is our parallel force. Remember, this angle is the same as this angle. And so that makes this the adjacent side, and it makes, I can move this over here to complete my triangle. It makes the parallel the opposite side. If we go back to our mathematical functions, remember that the adjacent side uses cosine. And again, if you can't remember, you can look them up. The opposite side uses the sine. So if we put our stuff together here, what we want to do is to say cosine of our angle, which is 24, times this 19,000. Again, this 19,000 is our hypotenuse because it's going straight down. Straight down is our 19,000, and it's across from our right angle that we have here. And so I'm going to multiply that times the hypotenuse. And that should give us our perpendicular amount. If we do the same thing with the sine, that should give us our parallel force. And if you want to put those in the calculator, we should get the correct answers. You want to take a moment and do that. So I've got these worked out on the next page. On this next slide, it's a little bit fuzzy. But again, you can see you get the answers like this: 17,000 newtons for the perpendicular part. And we would get, looks like 2,700 newtons in the parallel. And again, as this angle increased, we would notice that this arrow should get longer and then this arrow would get shorter. as the forces would kind of change and move to the other side. Another example question, again, it's basically, there's nothing different about doing these again. So if I have a ramp, I've got an object on the ramp, I've got a 1.65 Newton truck. That's going to be the weight pushing down. All right. And again, it's on a 27-degree incline. So if I draw the perpendicular force, and I draw the parallel force, actually I should probably draw it about right here. Again, that's where our right angle is going to be. Again, just to kind of change the color up. If this is 27 degrees, then this is also where my 27 degrees is. These are mathematical equivalences if you want to trust me on that one. So if I've got the 27 degrees at this angle and I'm trying to find the perpendicular force, again, this is going to be the adjacent side. So adjacent uses the cosine. Again, look at your reference sheet if you need to. But again, we'd have the cosine of 27 degrees, and we're going to multiply that times the hypotenuse, which in this case is 1.65. And that should give us the force that's pushing into the ramp. And then if we want to get the parallel is going to be on this side. That's going to be our opposite side, which means that we're going to use our sine function. So put it in the calculator exactly the same. Sine of 27 times 1.65, and that should give us the parallel part of this. All right. Again, pause, rewind, go back and look at it if you need to. But again, it's just trigonometry, sines and cosines like we have done before with some other types of things. So hopefully by the time we finish this up, again, here's how it's worked out if you want to see it with the actual answers that we have on there. Again, inclined plane is a ramp. When we draw these out, we're going to draw the weight straight down. We're going to have a parallel force that's going parallel to the surface. We're going to have a perpendicular force that's perpendicular to that. You should also draw a normal force that's going up from the perpendicular. And then we can use our sines and cosines in order to be able to kind of figure out which components, what the forces are on each of the components given the weight of an object.